Welcome to this edition of Models 2 ACE. Presenting an Excel spreadsheet-based model to arrive at the best possible combination of values of a set of decision variables for meeting a certain set of goals, with distinct order of priorities, in the best possible manner. Using Iterative Goal Programming. Let us revisit the difference between goal programming and linear programming that we demonstrated in the videos on linear programming model for optimal assignment and on optimal activation of benefit provisions for employees. Linear programming, or LP, helps us to strictly meet each one of a certain set of goals under a certain set of constraints. Typically, LP has one objective which has to be maximized or minimized. This maximization or minimization is subject to a set of rigid constraints. On the other hand, in goal programming, while the constraints are still there, it is clear beforehand that it won't be possible to meet each one of the present set of goals. Therefore, we will need to compromise on one or many of these goals, while ensuring we have the best possible solution for our decision variables. Consequently, in preemptive goal programming, there are multiple objectives. These are prioritized and arranged in order of priority, starting with the highest priority, going all the way down to the lowest priority. These goals are not necessarily rigid rules. Thus, unlike an objective in linear programming, a goal, in goal programming, may be overachieved or underachieved. When we shoot past a target goal, overachieving it, the deviation is positive and is denoted by P. When we fall behind a goal, the negative deviation is denoted by N. So, if target T1 is overachieved by a value P1 and underachieved by N1, though both not necessarily simultaneously, the resultant target value is T1 plus P1 minus N1. Note that a deviation, such as N1 or P1, is always to be minimized, whether it is positive or negative. Based on the nature of the goal, that is, whether it takes us in the direction of our objectives or away from it, we decide to minimize either N1 or P1. For example, if T is total capital expenditure, we would aim to minimize the overachievement P1. So, we have a pecking order of constraints and goals. At the top of the order are the natural or functional constraints of the problem, such as integer constraints, ceiling or floors on certain values, etc. Any constraint always has a higher priority than any of the goals. Next, are the set of goals, under the first order of priority, P1. We attempt to meet these goals with the highest priority, in the first iteration of optimization. The constraint set is same as the functional constraints of the problem, described before the set of goals. Third, we attempt to meet the goals under the second order of priority, P2, in the second iteration of optimization. In this iteration, in addition to the natural or functional constraints of the problem, the bounding condition for the constraint optimized under P1, is operative and further limits the space of feasible solutions. So, the goal under P2 may not be optimized to the maximum extent that would have been possible, if this were a linear programming problem, where P2 would have been treated on par with all other constraints. Similarly, when we attempt to meet the goals under the third order of priority, P3, in the third iteration of optimization, in addition to the natural or functional constraints of the problem, the bounding condition for the constraints optimized under P1 and P2, become jointly operative and further limit the space of feasible solutions. This process goes on, until the goals under the last priority are met to the optimum extent possible, under the most restrictive set of constraints and boundaries afforded due to the higher order priority goals taking precedence in optimum. A boutique shopping mart Sunshine wants to launch a wave of promotions to attract footfall to its facility at Millionaire Park. It plans to engage a marketing firm Cognic Incorporated to undertake promotional activities. Cognic Incorporated has offered to launch 3 campaigns, a targeted promotional campaign through text messages delivered to prospects' handheld devices and placement of advertisements in niche magazines and websites that garner eyeballs from the targeted segment. These will be carried out every month. round a year. The marketing manager of Sunshine has been clearly directed that not a single prospective customer must be missed out in each of the 3 waves. Cognic Incorporated has offered various graded slabs of the 3 packages. Each progressive slab of package increases in targeting accuracy, and differs in terms of the upfront cost of purchasing the package as well as the monthly expenses incurred in operationalizing the waves of promotion. Accuracy of targeting is very important, as otherwise, Sunshine would end up attracting non-prospective targets to Millionaire Park, who would then end up visiting its neighboring competing mart, Black Hole. Only accurate targeting would ensure attracting the appropriate segments of customers who would have only Sunshine Incorporated in their consideration, and not Black Hole. This has the single greatest impact on campaign ROI. A shotgun approach would end up attracting the masses, which would end up visiting Black Hole, since its offerings straddle across large segments. However, these segments do not have the boutique Sunshine in their consideration set. Sunshine has calculated a leakage ratio metric for each package, which is the percentage of wrong targets reached out to by the campaign, which would end up visiting Black Hole. Cognic Incorporated offers 18 slabs of the text messaging package that have the required reach for Sunshine. The lowest slab costs €30,000 and has estimated annual operational expenses of €15,000. It has a leakage ratio of approximately 19%. Each higher slab reduces the leakage ratio by 1%, but costs an additional €5,000 over the previous lower slab to be purchased, apart from increasing the operational costs by €5,000 per year. The lowest, among 8 slabs, of the magazine advertisement package costs €20,000 and imposes operational expenses of €10,000 per annum. Being a basic offering, it has limited targeting capacity and has a leakage ratio of 20%. Its ROI would not only be low, it would end up feeding competition at the company's expense. Higher slabs progressively increase in targeting accuracy. Each higher slab costs €10,000 more than its preceding lower slab, bumps up operational expenses by €5,000 per year, but reduces leakage ratio by 2%. Finally, there are 9 available slabs of the website advertisement package. The lowest costs €10,000 and imposes operational expenses of €10,000 per year. It has a leakage ratio of 25%. Each higher slab costs €1,000 more than its preceding lower slab, bumps up operational expenses by €1,500 per annum, but reduces leakage ratio by 3%. Finance has given the guideline to plan for a total expenditure of €150,000 for all 3 packages taken together. This immediately ruled out using the most expensive slabs of the 3 packages. Let us walk through the sections in the spreadsheet-based model. This is the first tab, titled Model Parameters. These tables indicate the goals desired to be met, along with factors contributing to advancement of the goals and relative priorities among goals. The marketing manager of Sunshine has been mandated to achieve the following goals, in reducing order of priority. Priority 1, the total leakage ratio for all 3 slabs of the selected packages, taking together, must not exceed 20% per target. Priority 2, attempt to restrict the budget to be used for purchasing all 3 packages to €150,000. Priority 3, plan to hold down the average total operational expenses for the 3 packages to €90,000 per annum. Summarizing the Model Parameters tab, we have the section on the marketing goals for Sunshine and the section listing out the priorities of the stated goals. The next tab contains the model that decides on selection of the mix of packages, optimizing factors against these goals. Proceeding to examine the next tab, titled Model, Goal Optimization, this table presents the details on the 3 marketing channel packages. This range of cells, named array selected _ slabs using Excel's name manager, is where the selected slabs for the 3 packages are indicated. For example, this value of 3, in cell E6, indicates that slab 3 has been chosen for the website advertisement package. These gray color ed cells indicate floor and ceiling constraints on those slab numbers. Clearly, the lowest value that these numbers can take is 1, denoted by these greater than or equal to conditions and these floor values of 1, collectively named array lowest _ slabs. Similarly, the gray color ed cells to the right indicate the upper bounds, corresponding to the highest slabs available, and named array highest _ slabs. The sum of these upper bounds, 18, 8 and 9, is 35. Obviously, these slab numbers must be integers. These values are the primary decision variables, and will be produced by our optimization model. Launching Solver, we verify these functional constraints under the Constraints section. This constraint stipulates that the values of the selected slab numbers must be integers. This constraint stipulates that these values must be greater than or equal to 1, denoted by array lowest _ slabs, and lesser than or equal to the highest slabs, denoted by array highest _ slabs. Since selecting the most expensive slabs of the 3 packages has been ruled out, we stipulate a constraint that the sum of the 3 slab numbers, named SumSlabs _ selected here, must be less than the ceiling of 35, i.e. the sum of these 3 slab indices must be strictly less than 35. Since linear programming conditions must be modeled as less than or equal to conditions, we change the right-hand side of the strict equality to the next lesser number, that is 34, and change the sign to a less than or equal to. You are wondering, why do we even need to specify this SumSlabs _ selected condition? Isn't this a redundant one, since the second budgetary goal would automatically select those values of the 3 slab numbers that restrict the total purchase budget to within €150,000? Please note that budgetary goal is a lower priority goal. The goal on total leakage ratio has the highest priority. So, when this highest priority goal is being satisfied, the next lower priority goal, which is the second goal on total purchase budget, is not even under consideration by the model. Hence, to have the SumSlabs _ selected condition operant even when the second priority goal is not being considered, we must have this SumSlabs _ selected condition fed as a constraint to the optimization model. As any constraint always has a higher priority than any of the goals, the SumSlabs _ selected condition would always be operative and will be attempted to be satisfied by the model before moving to the goals, if included as a constraint to the minimization problem. These values indicate the purchase costs of the lowest slabs in the 3 packages, and these values denote the marginal increase in purchase cost for each higher slab in the same package. Thus, the final landed cost of a selected slab, such as the slab 3, here, for the website advertisement package, is the sum of the base cost of the lowest slab plus the increment applied for each additional higher slab. This -1 is applied to exclude the base slab, which is already included in this basic cost. Similarly, these values indicate the annual operational expenditures of the lowest slabs in the 3 packages, and these values denote the marginal increase in OpEx for each higher slab in the same package. These values denote the final landed OpEx of the selected slab. Finally, these values indicate the leakage ratios of the lowest slabs in the 3 packages, and these values denote the marginal increase in leakage ratio for each higher slab in the same package. These values denote the final landed leakage ratio of the selected slab. This table constructs the list of goals, using the values tabulated in the table above, arranged in reducing order of priorities. This column lists out the actual levels of the goals achieved, based on the slabs selected here. For example, this value, denoting the total leakage ratio, is the sum of these computed values of these leakage ratios, named array leakage _ ratios, here. Similarly, this value, denoting the total purchase cost, is the sum of these computed values of these purchase costs, named array purchase_costs, here. Finally, this value, denoting the total operational expenses, is the sum of these computed values of these operational expenses, named array maintenance_costs, here. These values indicate the deviations of these actual achieved values of the goals, against the targets, specified in these cells. For example, this value, 56, of total leakage ratio exceeds the targeted value by 36%, denoted by this value of 36%, under the column overachieved. This value of 78,000 is short of the maximum stipulated value of 150,000 by 72,000, denoted by this underachieved value, here. These values again, will be decided by our optimization model, and form a set of decision values, shaded green, here. All these decision values, are shaded green. The actual values achieved and these deviations from the targets, taken together, add up to these values under the column balanced equation. Obviously, these values, collectively denoted by the named array, or balanced_equations, must equal these target values, denoted by this named array, ARR targets. Launching solver, we observe that this constraint has been recorded, here. Solving for the goal under priority 1, in the first iteration, since the total leakage ration must be confined to the target value of 20%, this overachievement must be minimized. Launching solver, we set the objective function of the linear programming algorithm to this value, in cell M11, named leak ratio_over. Note that, at this early stage of optimization, we would not want to enforce the integer constraint on the slab numbers, as that would severely restrict the space of feasible solutions for upcoming iterations. Under solver options, we check the box next to ignore integer constraints, for this first iteration of optimization. We now launch solver, select the option to make unconstrained variables non-negative and select the simplex LP method for deriving the solution. We now instruct solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that solver has generated. The solution suggests that we select slab number 3 for the package on text messaging, 8th slab for magazine advertisement and the 9th slab for website advertisement. This leads to the optimized value of 23.6% for the level achieved under the leakage ratio, resulting in the target of 20% being overshot by this value of 3.6% for leak ratio_over. Now, moving on to the goal under priority 2, in the second iteration, since the total purchase cost must be confined to the target value of 150,000, this overachievement must be minimized. But, since this goal is under a lower priority 2, it must be optimized in such a way that this optimized value of 23.6% for the level achieved under the leakage ratio or overachievement of the target of 20% by 3.6% must not deteriorate any further. Launching solver, we set the objective function of the linear programming algorithm to this value, in cell M12, named purchBudget_over. We create the additional constraint that leak ratio_over must be less than or equal to the optimum of 0.036, obtained under the first priority. We also maintain this value of 0 for underachievement in leakage ratio, as an additional constraint. But since the non-negativity constraint is in force, we can specify this as a less than or equal to 0 condition, since an inequality is of a lesser complexity than a strict equality constraint. We now reinforce the integer constraint on the slab numbers, by unchecking the box next to ignore integer constraints. We now instruct solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that solver has generated. The model suggests that this value of purchBudget_over cannot be optimized beyond 3000, while still meeting the goal under priority 1. Now, moving on to the goal under priority 3, in the third and last iteration, since the total operational expenses must be confined to the target value of 90,000, this overachievement must be minimized. But, since this goal is under the lowest priority of 3, it must be optimized in such a way that these overachievements under the 2 higher priorities must not deteriorate any further. Launching Solver, we set the objective function of the linear programming algorithm to this value, in cell M13, named OPEX_over. We create the additional constraint that purge budget_over must be less than or equal to the optimum of 3,000, obtained under the second priority. We also maintain this value of 0 for underachievement of total purchase cost, as an additional constraint. But since the non-negativity constraint is in force, we can specify this as a less than or equal to 0 condition, since an inequality is of a lesser complexity than a strict equality constraint. We now instruct Solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that Solver has generated. The model suggests that this value of OPEX_over cannot be optimized beyond 7,000, while still meeting the goals under the higher priorities 1 and 2. Summarizing the optimal channel mix produced by the model, the 2 sets of decision variables, contained in the cells shaded in green, were the decision on slabs to be operationalized for the 3 packages, and the deviations in total leakage ratio, total purchase budget, total OPEX. The consequences of the decisions on the slabs were the actual levels of purchase cost, leakage ratio, and OPEX. Consequent to these were the positive or negative deviations from the goal targets, also in cells shaded in green. For each iteration, the objective function minimized the deviation from target for the current goal. Thank you for giving Models 2As the opportunity to serve you with our analytical models. Please subscribe to our channel for more.